In this video, I will give you one of the most simple examples of how to use Lagrange's equations. What I have here is a string that masks the white line. This is a string that passes over a pulley, and I have the mass 1, mass 2. I have chosen the coordinate system so that the origin is at the center of the pulley, plus x plus y. And I am specifying the position of m1 with y1 and the position of m2 with y2. They're both on the y-axis. And of course, since they're only moving up and down, the only thing that changes is their y position. Their x position stays constant. Now, because the string, the rope, has a fixed length, I know if I add whatever this is, and this is equal to minus y1, since y1 is a negative number, with minus, I'm going to get the length of this part of the string, plus the minus y2 is going to give me the length of this part of the string, plus half of the circumference of the circle, so pi r, will give me the total length of the spring. And with this L, this is the length of, not the spring, the string. Okay, and this is an important relationship to keep in mind. We will use it. Now, moving on, I need to find the kinetic energy of the system, and in this case, the system will include mass 1 and mass 2. So I have 1/2 m1 and v1 squared plus 1/2 m2 v2 squared. Now, because they are only moving up and down, really this is the y component of the velocity. So it will be 1/2 m1 y1 dot squared plus 1/2 m2 y2 dot squared. Now, there is one way that I can make this expression a little bit more simple. I know I am aware of this constraint and I can use it. And I can use it in the following way. I can take the time derivative of all of these. So minus y1 dot minus y2 dot. That's a constant, so the time derivative goes to 0. That's a constant, the time derivative goes to 0. And this means that y1 dot is equal to minus y2 dot. So the time derivatives are opposite. I can use this to eliminate y2 dot from here, and this will be 1/2 m1 y1 dot squared plus 1/2 m2 minus y1 dot squared. Now, this is the expression for the kinetic energy. The potential energy for the system, m1 g y1 plus m2 g y2. And what I will do, again, in a similar fashion, I will use the constraint. So y2 will be equal to minus y1 plus pi r minus L. And this becomes m1 g y1 plus m2 g, nope, there's a minus sign, minus m2g y1 plus m2g pi r minus m2gl. This is the potential energy for the system, and now that I have those two, I can find the Lagrangian. And it will be 1/2 m1 plus m2 times y1 dot squared. I combined those two terms minus the potential energy, so it will be minus m1g y1 plus m2g. I could combine those two, but anyway, minus m2g. How about I just leave it as pi r plus L. No, that needs to be a minus. Alright, so that's the Lagrangian, and now the variable that I'm using is y1. And I'm gonna find those two partial derivatives first. That's not dependent on y1. These two are dependent on y1. That's a constant anyway. So this will be minus m1g plus m2g, and then here the only term that depends on y1 dot is this one, and the 2 will cancel out with 1/2. So I will have m1 plus m2 y1 dot. Now using all of those three, what I get is m2 minus m1 times g is equal to d over dt m1 plus m2 times y1 dot. And because m1 plus m2 are constants, the time derivative will essentially change this to a y1 double dot. So I will have m2 minus m1 times g divided by m1 plus m2 is equal to y1 double dot. This is the acceleration of mass 1, and once I know the acceleration and the initial conditions, for example the initial position and the initial velocity, I can move on and predict the motion. But this is the acceleration. If I want to find the acceleration for mass 2, I know that the two are related with this expression, so I can just with a minus sign, I will also be able to know what is the acceleration of 2.